Thank you all for coming. So I think the topic is, you all know, since presumably that played some small role in persuading you to come in. Like all topics in physics, if you start to look, there's a precursor of precursors of ideas that go back a long time. And so topology already showed up in classical physics. You've seen fluid vortices. The great Poincaré used topological ideas in thinking about chaos. So everything does have a precursor till you get back to the bacteria. Who knows, maybe even they were using topology in some ways that we don't yet understand, but will soon once the next model from OpenAI is out. But in my own field of condensed matter physics and that of my colleagues today, we tend to think of sort of the discovery of the quantum Hall effect as a point where condensed matter physicists really began to have topology as a main item in their arsenal. It existed previously in the so-called topological theory of defects that I'll talk about a little bit, but then it really took off. Then it sort of went dormant for a while, and then there was the discovery of the so-called topological insulators, which essentially extended the Hall effect to a much larger class of potential phenomena. All of this then goes along with, this is sort of single particle physics, and then there's a lot of many body physics, and so on. So meanwhile, there are parallel developments in quantum field theory used by particle physicists, again, starting in a big way in the 70s, terms like solitons, instantons, a lot of actually beautiful mathematics done at Oxford with Michael Atiyah and people around him in parallel with quantum field theory, and of course Roger Penrose in the context of other problems. So that said, you should think of today as sort of my job is to introduce a few ideas. I teach an 8-week course in the Masters in Mathematical Physics. So this is the compressed version of it. Right? And then my colleagues who are much more active and working on things at the cutting edge at the moment will tell you about things which are more substantial in terms of cutting edge physics. Very good. So with that, I guess all I need is some sort of does this work? All right. Okay. So we start with the question of what is topology, and so of course informally, right? Topology studies properties of objects, ultimately mathematical objects, which remain unchanged under continuous deformations. So topology is prior to doing calculus. When you have functions that, things which have to be smooth, so you can do things like take derivatives. Topology doesn't demand that you be able to do that. And so, of course, the example that everybody trots out is that a coffee mug can be continuously deformed into a donut. And here is from Wikipedia, with that particular maneuver. So as you can see, the first thing you do is you take the coffee mug and you raise the bottom all the way to the top. It's not very useful as a coffee mug anymore. And then you smooth it out, and there's your donut. Now, as Andre said, the topological education of physicists, and I belong, like him, to a generation that this was not standard. So I can't say that I have a, proper understanding of the mathematics. I don't. Physicists are often described as recreational mathematicians. I think it's not wrong. Pragmatic mathematicians may be the other way, which is right. But in any event, there is a question in mathematics. So when you see pictures like this, then these pictures are in our three-dimensional space, so they are sort of embedded, whereas mathematicians also distinguish between what happens if you talk about objects without thinking of them as being embedded in anything. Right? So there are sort of more abstract ways of doing it. So to go one step in that direction is that, topology tries to classify topological spaces up to homeomorphism. So the usual problem of starting to read mathematics, which is with every definition, there are another three things that you realize that you don't know, right? So in this case, what's a topological space? What's a homeomorphism? All right, so homeomorphism is a continuous bijective map with a continuous inverse. We won't need it today. But a topological space is this, some set of points where there's some notion of closeness, but you don't have the notion of a distance, right? You're not allowed, you don't need to have a metric which says I get from here to here and it's, this distance. But simply that things are close and things are far. And once you do that, you can have limits, continuity, connectedness, and so on. So, okay. Now, you might say, what would this have to do with physics? So obviously in physics, units are important. You've all, maybe, I assume, perhaps almost all of you have been physics undergraduates, and one thing that would have been drummed into you is units. How come you wrote 6? What units, right? I mean, you're physicists, you have to know what units are, and then maybe on top of it, dimensional analysis, right? And so on and so forth. And why do we think there's something may happen at the Planck scale? Well, there are units, you combine them, so on and so forth. So it seems a little odd to say, let me start talking about stuff in physics which doesn't have units, right? So you might say, well, surely this is irrelevant. But so I have to sort of tell you, I tell you that topologists classify spaces, so you might say, what spaces are interesting in physics? Well, so it could be real space. Now, of course, the space we live in is what it is. There are cosmologists, I think, who do wonder periodically whether the universe itself is a giant donut in 3 dimensions, but we're not talking about that. As a condensed matter physicist, we actually do sometimes ask the question, well, what would happen if our condensed matter system was put on spaces of different topologies? So in the case of the quantum Hall effect, the fractional quantum Hall effect, you say, does it live on a sphere? Does it live on a torus? Does it live on a donut with 2 holes? It's not something that would happen in the laboratory, but it's a way of asking a certain question about the system. And it turns out, for example, that the 1/3 quantum Hall state will have 1 state on the torus, 1 on the sphere, 3 on the torus, and 9 on the next one up. And that's a way of discovering that state, which otherwise looks like a liquid, has something special going on inside. The next one up is momentum space. So this requires that you have been forced to sit through solid-state physics. I hope you were. And so you may remember things called Fermi surfaces and Brillouin zones. So in the spherical one is that of sodium. And so that just looks like a sphere. And notice that it sits inside this wire cage, which is the Brillouin zone. So that's the unit in which things are going to repeat in momentum space. So you'll have 1 sphere and a second and a third, but they won't touch each other. But the next one for copper has these black things, which are actually pipes connecting to the next Brillouin zone, which have been cut off to display it. So if we actually plotted the whole thing, you would have this thing extending through momentum space with all these tubes connecting neighboring cells. So you can see that the topology of the two is different. In one case, there are, you can surround a sphere and disconnect it from everybody else. In the other case, they're just pipes all over the place. Looks like the basement of a particularly, difficult building. Okay. Then you could say, well, what about, spaces of trajectories? So this will come up in Steve's talk, that you should think of these as identical particles, quantum mechanically identical particles. So here they are initially, and here they are at some later time. And along the way, if we insist that they cannot be at the same point at the same time, which for fermions is standard, but let me say there are other particles, and indeed these will be the anyons of his talk, for which this is true, then you can sort of see that this is like taking bits of string and, kind of maybe braiding them around another and reconnecting them at the top. And, you can't simply, there's something stable about that, because once you've scrambled them up a bit, braided them a bit, you cannot unbraid them without really taking them off the hooks at the top. And so the space of trajectories can be another one which has topologies, and that will show up today. Then up the food chain, there are things called fiber bundles. And while this picture is useless for the purposes of actually doing anything with fiber bundles really, but it is roughly the idea, which is you have some base manifold and then these things which have been drawn as fibers. But the main point is there is a space for physics, it could be, for example, real space, and the fiber is something that lives at that point. So you've all done Maxwell theory, electric and magnetic fields. So think of real space as the base manifold and the electric field at a point or the magnetic field at a point as living in the fiber. And then that's the space. And it could be space, it could be space-time. So this could be a space whose topology we're interested in. Then you could have extended objects in condensed matter physics. There are vortex lines, vortex loops. You could even make them up in gauge theories. There are things called Wilson loop operators, extended operators. And in fact, again, Steve may not bring them up, but some of the things he'll talk about, you calculate them mathematically as Wilson loop operators, and you're interested in questions such as, do they link or do they not? And actually, do they not? KN, OT, which is a beautiful subject. All right, so that's basically to explain that there are lots of settings in which you would be interested in the topology of some space that is relevant to physics. That doesn't mean that the physics of distances has gone away, of units, that's there. So sometimes there is a specific term that you're trying to calculate, which is not distance dependent, but is topology dependent. And occasionally you get lucky and the whole answer depends upon the topology and nothing else. But that's more rare and of course more beautiful when that happens. All right, so as a subject in mathematics, topology has all sorts of tricks up its sleeve. So of course, ideally you could just be completely confident whether there's a homeomorphism or not, but topologists, especially that talk about very, very abstractly defined spaces, have come up with ways of thinking about them which are somewhere partial. You try and decide whether two spaces are the same or not, depending on asking some more limited question of them. So one of the techniques goes under the topic of homotopy groups. This is actually not the one that turns out to be mathematically the easiest to do, but it's the one that's easiest to explain. So basically, in homotopy, what you do is you have your space sitting somewhere that you're interested in, and on the right-hand side, you put down spheres of various dimensions, right? So let's start with the simplest, it's not the simplest one, but let's start with the second simplest one, which is a circle, then the sphere in our dimensions, and then, of course, you go up in one more dimension and one more dimension, one more dimension. Having done that, you consider a map from this thing that you've put down here to the space of interest, right? So there's some functions you can write, and you want these functions to be continuous. But then you ask the question, how many different types of functions are there? And what's the definition of type or equivalence class? It's that if you can deform one function continuously into the other, you say they're the same, right? And if you can't, now you have a new object. So this is a sacred maneuver in mathematics, that you look at equivalence classes of objects, and having done that, then you're often interested in how do the equivalence classes, do they compose? Can you multiply them, and so on and so forth. And in the case of homotopy, which it will turn out that these equivalence classes will have a group structure, and if you go from Sn, the sphere in n dimensions, to space, those are called that will be called the nth homotopy group. All right, so we will use the first and the second, which are and then stop. I know a little bit about Pi3, but after that I have no clue what's going on. All right, so if you're mapping from a circle to some space, so let's say the space is sort of our room. A map from the circle is to draw a loop on the space that you are going to. That's essentially what it means, because each point is mapping somewhere, because the circle closes on itself. Any loop that I draw in the space has to close on itself. So far, so good? So what we're asking is, you have this space, unknown space, we call it X. How many different types of loops can you draw on it? That is what the first homotopy group is going to tell you. Okay. So if we are looking on the plane, right, so if I'm, let's say on the blackboard, if I draw something, you can always shrink it to 0, right? It doesn't matter what complicated thing it is, you just sort of continuously keep shrinking it, and it'll be down to a point, then you can get rid of it. But something interesting happens if we decide to exclude one point from the plane. So here it is, the black dot is gone, it's a hole in the plane. So now, I could have had a curve here, that I could shrink to 0, but the moment I've gone once around it, it cannot be shrunk to 0. If I go twice, I can't shrink it to this, I can't deform it to this, and likewise, right? So the number of times, think of carrying a piece of rope, walking around and sort of stretching it out, right, and then tying it at the end, as long as you are living on the plane yourself, right, you're not allowed to jump over it. You can't unwind it, right, once you've tied it. So that tells you that the first homotopy group of the plane with the point removed is the integers, because, and then to compose them, you just do one, and then you do the second following, and that's called multiplication, and in that, it looks like addition here. Sorry, I seem to have lost, sorry. The last line says the following. I said it for a plane with the point removed, but actually most of the plane was irrelevant. I can just shrink the rest of the plane and basically just talk about a circle. I can expand the whole, and so on. And so if you say you're going to draw loops on a circle, that's also the same classification, right? You go around the circle, either you don't go around once, go around twice, or go around -1 the other side, -2 the other side. So far, so good? So that's the meaning of saying that maps from the circle to the circle are classified by the integers. So this is a simple example, right, of a topological construct. What can we use this for? So we condensed matter physicists are often interested in things that look like magnets, either because they are magnets or because we've learned to map all sorts of things onto things that look like magnets. And so often we talk about models. So for example, there's something called the XY model. And what the XY model is XY because there's a spin, and the spin has to live in a plane, which we call the XY plane, therefore the XY model. And so now a ground state in a magnet, ferromagnet, is one in which all the spins agree on what to do. Right? So every spin will point in the same direction. I'll show you a picture in just a second. But then, if the energy is not minimum, the spins will deviate from this exceptionally happy configuration. Right? So many things can happen, but one of the things that can happen are what are called topological defects, which I'll just describe in a minute. And the claim is, in the XY model, the topological defects are classified by pi1 of S1, the first homotopy group of the circle. So how does this happen? So here's the ground state, right? So everybody's pointing the same way. Now, this is an example of a spontaneously broken symmetry, which means that while I've drawn it this way, really we could globally rotate every single spin. You can just take the picture, do this, do that, and that's an equally allowed configuration. Right? I'm imagining rotating the spins, not the space in which they live. So that axis, the fact that they're pointing up, is just a particular choice. Really, they could point in any direction. But the important thing is that in the ground state, they all agree. The energetics of a magnet, of a ferromagnet, says to each spin, try and agree with your neighbors. Okay. And an antiferromagnet, in the simplest case, the instruction to each spin is try and disagree with your neighbors, which looks a bit more like American politics, which is my country of citizenship, so I'm allowed to say. Okay, good. Very good. Now, you could make deformations of this. If I said, raise the energy, you could say, you could take a given spin and you could move it a little bit, and you would say, I should expect to end up with a higher energy, and you would. But there are particularly interesting things which you can do, which are very hard to get rid of, and that's where the topology comes in. Okay. So here's a vortex, right? Of course, you know them from fluids. But I want to explain what this has to do with the topology that I was describing. So the first thing is a defect, by its name, suggests something doesn't look right somewhere. So in this case, something doesn't look right at the middle. So let's ignore that. If we go far from the nominal location of the defect, what we expect to find on energetic grounds is that at least locally, this configuration should look like it's in a ground state, right? Because that's the state of minimum energy. And indeed, if you look at this picture, you will notice that if I only gave you a small snapshot of this, you would say the spins are all pointing up. If I said this, you would say to the left, down, to the right. So locally, I have something that looks like a ground state. But there's this aspect that globally, even very far, the spins are not all agreeing, right? So they sort of slowly twist. And in fact, we could do it mathematically. If we go farther and farther out, we can write down a configuration in which that, energy can be calculated. So given the assumption, which is energetically justified, that far from the location of the defect, the system must locally be in a ground state, we can now ask the following question. We can say, go very far away and walk around the defects. What do you see? So observe that you're walking in a circle. That's your S1 from which you are mapping. Locally, you see a direction of the spin. The spin itself lives on a circle. That's the S1 to which you are mapping. And what do you see? If you walk clockwise, you find that the spin rotates, anti-clockwise, the spin rotates anti-clockwise. Of course, clockwise, right? If we go back to the ground state and we do the same thing at infinity, what do we see? The spin doesn't rotate at all. So the ground state is characterized by the trivial map in which every point, maybe I should just draw this here. So this is the S1 from which I'm mapping. This is the S1 to which I'm mapping. So the ground state consists of mapping every point on this circle to a single point in that circle. But the vortex consists of mapping every point, right? And you'll see this theme recur to the identical point, right? And these two are in different topological classes. Small deformations of these maps cannot take you from one to the other. You have to do something pretty major. You either have to take your string around the hole or you don't, right? And you have to cut it in order to do it that way. So what you can say is quite generally that if you have an XY system and you're in 2 dimensions and you have a defect, if you walk around it at very far away, you should be picking up some element of the homotopy group. We've seen the 0 and 1. And if you want to know what 2 looks like, well, here it is. Again, don't worry about what happens in the middle. Just focus on what happens at the boundary. It points to the right, left. See that it's returned to itself, although only gone halfway. And then it will repeat. So it will rotate twice for each circle at infinity. And that will become the element corresponding to the the integer being 2. And then I can draw pictures in which you go clockwise, and the spin rotates anti-clockwise, and then that will give you negative numbers. So now, the reason that the topological stuff is interesting is that because we know that you can't continuously deform one of these maps into the other, it shows you that if you had such a configuration and you looked at it at infinity, you could be confident that you can't just, by flipping a few spins, you can't get to the other one. You've got to do something very, large scale. Now, in physics, the energy, if you have a system of a certain size, the energy is something finite. So sometimes I like to say that, topology proposes, but energetics disposes. This being physics, right? And that's true, but nevertheless, topology gives you a very good idea that some things may be very, very hard to do. Okay, so now there's a much fancier topological theory of defects, which, liquid crystals, things like that. Obviously, the utility comes when you use mathematics to find things that, you couldn't just have said by just looking at pictures. And trust me, there are examples like that. All right. Okay. So I want to use this homotopy for one more thing. And are you all able to see the board more or less? No?
It's invisible. I think you need black.
Okay. And where are they? This is good? All right. So let's do that. Okay. So far, this was kind of classical, right? Classical in the sense of just doing energetics. I now want to show you that the same sort of stuff can enter quantum mechanics. So I'm going to consider particle on a circle. Is this readable? No, not really? Okay. Okay, what? Okay. So this is why I mostly opted to do slides. Anyway, you don't really need this. It's a particle on a circle. Let me try and do something bigger. All right. How about that? Any better? Yes? Okay, good. Excellent. Were you all this enthusiastic when you were in classes as young people? All right. So here is the location of the particle. Just to simplify, let's take the circle to have radius 1. Okay? So the circumference has length 2 pi. The particle is here, and we will say, well, at time t, it's at some location theta of t. And then it's going to go from theta of 0, it's going to be some initial theta, and theta of t is going to be some final theta. So we're going to start somewhere, end somewhere, right? Okay. So in classical mechanics, we're just going to do a free particle. And since the radius is fixed in 1, distance and angle are the same thing, although the units have to be different. So when you write your homework solutions, I will penalize you for those, but I myself am going to ignore units. All right, good. So that's our free particle Lagrangian, half mass times the velocity squared. And as you'll recall, what we want to do is we want to write the action and then extremize it subject to these two conditions, right? So that's classical mechanics. Now, we can derive the equations of motion from this, and they're just going to say that the mass times the acceleration has to be 0 because it's a free particle. All right. Now, one thing about the particle living in the circle, as we just discussed, is that it can start, so let's say this is theta I, and this is theta F. So it can certainly do this, but it could also do that, or go around a certain number of times, right? So actually, this is one of these cases where, many trajectories are possible for the same sort of initial and final conditions. In fact, sometimes it's simple to simply take the final condition to be the initial condition just for analysis, in which case there's a solution in which you just sit there. That's the bureaucratic solution. And then there are solutions of, I get the feeling that this particular audience is not as hostile to bureaucratic inertia as some of us have come to be. All right, I can define something called the winding number, which is, I just integrate the time derivative, right, of theta dot. Now, you might be tempted to say, well, this is just theta f minus theta I, but because this is a periodic variable, this is not true. It's actually this plus 2 pi times n, which is the winding number, right? So that's because it's a multiply valued variable. Good. So now I claim that I can change this action to this plus some number alpha times w. And that's absolutely every bit as good a classical action as the one that I wrote down at the start. Okay, so if you remember dimly, you may remember that total derivatives don't matter for actions. If not, the next thing you can say is, well, if I have something like this, which I'm keeping the endpoints fixed, something that seems to depend only on the endpoints, can't matter because I can do my variation without this value changing. But in the worst case, you just pull out your Euler-Lagrange equations and you differentiate with respect to theta dot, you get a constant, differentiate with respect to time, you get 0. So literally, you get the same equation. So classical mechanics doesn't care whether I do this action or I add to it something that looks like that. But quantum mechanics isn't indifferent, because in quantum mechanics, what I'm going to do is I'm going to write a path integral which will take me from theta I to theta f, right, in some time t, and then I have to, let me put in this number alpha because it will matter. And the reason is that what you're going to do is you're going to say, well, this is a sum over all paths of e to the I s plus alpha times w. Now what I'll do is I'll take my paths and I'll break them up into parts of a given homotopy, right? A given winding number. And so I can say, well, this thing is sum over all winding numbers, e to the I alpha times the winding number, sum over the paths that belong to a winding number of e to the I s. And as you can see, this set of numbers, right, is going to be the same no matter what alpha is, but when I put in alpha, it obviously makes a difference. So what I discovered is that when I quantize this fact that my space was multiply connected suddenly pops up and tells me, you know what, your quantum mechanics is ambiguous. You have choices to make. And those choices are sensitive to this winding number. Now, of course, you know this in some other language. If I put a magnetic flux through the ring, right, it's not in the ring, it's not on the ring, but it's in the ring, and that's the Aharonov-Bohm effect, which says that, that flux is something that the particle sees. But this is something you can discover from topology. And then there are fancier field theoretic examples with topological terms. which do not look like putting a flux through anything, but you simply observe that the space has topology, you can write down such a term, and now you know that quantum mechanics can have such things. Right? The most famous example of that is the theta term in QCD, which is supposed to have all sorts of fascinating possibilities, although the state of the discussion involves axioms and so on, which is beyond my ability to go through. Okay, good. So far so good. So we've done 2 uses of pi 1 of S1. So I don't know how I'm doing in time because I may 5 minutes. So I'm nowhere close to, what was that? Oh, 20 minutes. Okay, oh good, done. Then I'm very good. Good. I really panicked there. Okay, I didn't practice, so I have no idea how this was going to go. All right, so let's go up and use the next homotopy. Right? So the next one is, we're going to use maps from a 2-sphere, the usual sphere that we introduced, and we're going to map it into the space of interest to us. Okay. So we will make the other space be a sphere, and you'll see how. So we are interested in the second homotopy group of the sphere. So maps from the sphere to the sphere. Okay. And it turns out that's also the group of integers, which, by the way, also means that the group is abelian. You can add them in whatever order. This is not always true of homotopy groups. You can certainly come up with ones which are non-abelian, where the order does matter. Okay. All right, so the index is going to be the number of times the first sphere wraps around the second sphere. So let's take a look. So here's again the trivial map. So the trivial map consists of simply mapping all points. What did I do with the? All points on the first sphere, which is the test sphere, onto exactly the same point, which of course I can pick to be anything. And as you can see, the entire area of the first sphere has been mapped onto 0 area on the second sphere. By the way, you know how I produced this? Because I'm absolutely hopeless. I went into ChatGPT and said, write me a piece of Mathematica code to do X, spat out Mathematica code, put it into Mathematica, produce this. Right? I did try earlier to say, I'm giving a talk tomorrow on the following topic, and it said in its usual cheery fashion, sure, what would you like me to do? So I dictated, a couple of paragraphs, and it produced slides. So in fact, I'm using the PowerPoint slides that it started with. Of course, I had to, because, it wasn't, it will be by next January, but this, and I'm not even kidding, but it produced a basic structure, it understood words, this, that, so on and so forth, and kind of stuff. So we're, a subject for a different talk, which I don't know if some of you may have noticed. I run a series on AI these days. The first one was with Dominic Cummings. Josh Simons is coming next. And so that's the parallel track of trying to keep track of what's going on in the world. But that said, that's how I produce this, but this is a trivial map. This entire area gets mapped onto 0. The next map, much as for the circle one, is this one, in which every point in the first sphere gets mapped to the corresponding point in the second sphere. And you can think of this, I took, basically I've wrapped the first sphere, just around that. And so the index is, it wrapped once. Every little area on the first sphere went to the corresponding little area on the second one, and so on. How do I get the next one? Well, so here's a picture stolen from Wikipedia. Okay, what's the picture? It's really, these two halves have to be glued together. They've been cut open to show you what's going on. So you took the first sphere, and you started wrapping it around the second sphere, but you go around twice before you're done. So if you go, it was like with the vortex, you went once around, right? And the spin rotated twice. So in this case, you go first around the first sphere, and you end up going twice around the second sphere on the equator. And in this case, you've chosen a particular axis. But of course, if you took the whole thing and rotated it this way, that would be a continuous deformation, and that would be a map of the same degree, right? So maps of the sphere to the sphere have this character, and that's the second homotopy group of the sphere. So far so good? So we're up to pi 2 of S2. Now the question is, what can we use it for? So we're going to use it for something which is close to what we did with the XY vortex, except it won't be a defect, it will be a soliton. So what's the difference between defects and solitons? So with the defect, as the term suggests, there's something wrong with it. And what's wrong with it is the region in the center where, spins are really moving in a way they really wouldn't like to, because energetically it's very costly. But far from the defect, they're behaving in the way that they would close to the ground state. Now, the reason defects are important is the topology, which is if you have one, it's stuck. You can't easily get it out. So even with solids, pieces of metal, right, which are so on and so forth, the whole, when you bend them and you have trouble, bending a piece of metal back, it's because you've introduced defects, which are then hard to get rid of. Right? So defects are very, very important because they're there, you can't easily get rid of them. Solitons are not defects. They have often similar sort of properties and will use the same topology, but things are everywhere smooth. So in this case, we're going to use pi2 of S2 to produce a soliton, a topological soliton. And they've come to be called skyrmions in condensed matter physics. They were actually nicknamed baby skyrmions because the actual skyrmions, due to Tony Skyrm, who I think worked not very far from here, were actually meant to be in one more dimension and with a bigger sort of space of spins, because he was thinking of how to get neutrons and protons, nucleons, starting from a field theory of pions. There's no point in getting into why he was trying to do it. It was a brilliant idea. It was ultimately completed by Ed Witten because the big challenge was how do you get Fermi statistics from things that you start off with which are bosonic. But anyway, hence the term skyrmions. So these skyrmions have the following property. We need two spheres, right, to map between. So the first sphere will be the space on which the soliton lives. And the second is going to be the space of fixed length spins, which unlike XY spins, now will be spins in 3 dimensions. So fixed length vectors in 3 dimensions live on a sphere, right? So you're going to map from a spatial sphere to a spin sphere. Okay. So this is going to appear in 2-dimensional spin systems and field theories. But now let me walk you through how that works. Okay, so first thing, let's assume that the space on which the spins live is literally a sphere, right? Well, that's not going to be true in a solid, but let's start with that. Here, by the way, same deal, ChatGPT to Mathematica. So here's the ground state. Spins agree everywhere, right? Again, I picked an arbitrary direction. It could have been, I could rotate all the spins in some direction and that would be just as fine. So this is, I've decorated, as it were, the spatial sphere with this. Okay. Then, this isn't quite right. So just ignore that. The way you're supposed to think about it, focus on this patch, is that at each point in the spatial sphere, the spin points radially outwards. So it's like a hedgehog, a perfect hedgehog, right? Okay. So this is a map in which each point on the spatial sphere has been mapped to the corresponding point on the spin sphere. This is topologically distinct. Small deformations of it, I could rotate, nearby spins a little bit this way, that way, won't change the fact that it's very far from the ground state where everybody was pointing the same. So far, so good? So we should agree. Now, this is not a defect. Everything is smooth. As you walk along the sphere, right, there's not a point at which you see that anything particularly violent is taking place. It's just slowly rotating. So this is okay. Now, the next thing I want to show you is that we don't have to have the system live literally on a sphere in order for this to work. We can actually descend to the plane, which is where you can find systems. And the way to do that is stereographic projection, right? So stereographic projection is going to tell us that, corresponding points on the sphere will be mapped to points on the plane, and the North Pole will eventually be mapped to infinity, right? But the thing we need when we do the stereographic projection, whatever the spin was doing at the North Pole will be what the spins will be doing anywhere at the boundary of an extremely large system. So in all directions, you should get the same answer. And if you have such configurations in the plane, you can compactify the plane, which is to say reverse stereographically projected to the sphere. And so then you can use the topology, which was so manifest on the sphere. So here's the ground state. Everybody points the same way. You go off to infinity, everybody points the same way. The next map, remember, was more or less, right, from each point. So the North Pole was going to go to the North Pole, the South Pole was going to go to the South Pole. So here's the skyrmion drawn on the plane. So the South Pole was the point of the origin. It's not perfect, but this thing is pointing down. And as you can see, as you go to infinity along any direction, the spin goes from being down to being smoothly up, and everywhere, well, it's almost up, everywhere at the boundary, the spins have pretty much recovered to being up. So in a magnet in the lab, or some system with this kind of order parameter, what you should then expect to find are excitations of the ground state, which locally have this structure. They look like particles because after a while, they recover, and these particles are called skyrmions. So the example probably which most completely sort of does what you want to do is actually in the quantum Hall effect. Funnily enough, it was my PhD thesis. And you get these particles, they actually have a charge, which in the case of the 1/3 Hall state is a fractional charge, 1/3 of an electron. They have a funny statistic, so they really, I think they would have made Tony Scrum very happy. They do everything. So they're genuinely new kinds of particles, but with this kind of description. Okay, so that came out of, now again, I said, topology proposes and energetic disposes. In this case, it turns out that the size of the skyrmions is itself actually can vary. They're not like defects. And the particular energetics of systems is important. And the quantum Hall effect, they end up having a nice, healthy size, which actually, if you tune parameters, you can make as big as you want. And then they are nice objects, and lots of their physics can be understood that way. All right. Good. So next up, and the last thing I'll do, is to use the same topology, pi2 of S2, to tell you something about how one gets fancy band insulators. So this is solid state 101. Just to remind you where bands come from, you start with, let's say, the dispersion of a free particle, which is a parabola, and then you put on a weak periodic potential, and that has the annoying habit of causing things to mix across a certain, right, momentum range, which is the inverse of the distance scale that you've introduced, and that causes gaps to open. And then you fold them and draw them this way, because once you don't have perfect translation invariance, and you are only translation invariant up to a certain distance, legally there's no reason for you to insist that there's something called a momentum. Momentum is a consequence of translation invariance, and if translation invariance is only due there up to a certain periodicity, then momentum is only defined up to that periodicity. And there's no meaning to drawing this separate from that, so you might as well draw it this way. Once you do that, what you have is that you have a set of energy bands, each one of these, and the energy bands are a function of momentum, but they have to be periodic. So, and you go up in higher dimensions, they have to be periodic in every direction of momentum. So if you take the underlying space here, which is momentum space, and you insist that things on it have to be periodic, it's as if the momentum lives on a torus. Right? So the Brillouin zones of solids are tori. In 1D, it's just a circle. 2D, it's a more familiar torus, and so on. Okay, good. Now, this is 1D, which is very special and kind of not that interesting, but once you move up from one dimension, interesting things can happen. So, for example, you can have that two of these bands are sort of there, and I can deform the Hamiltonian and do things to it so that states in here mix among each other. Maybe at some stage the gap closes, then it opens again. Well, I don't really affect stuff that happens further up. So for this reason, it's actually perfectly legitimate to think about what happens when you have a finite number of bands living on a torus. Okay? So this is when we get to that mathematics. And then so that's the next step is, for instance, we could consider 2 dimensions, and we could say just take 2 bands. And the thing I'm not telling you is that the way that the Hamiltonian of interest will always, this is single particle physics, independent particle physics, will factor at each point in momentum space, right? So because of that, what this formula is telling you is, consider a given point in K, consider a three-dimensional vector of unit length, and consider the set of Pauli matrices, sigma x, sigma y, and sigma z, and then this dot product gives you the most, all it's really telling you is the most general Hermitian 2x2 matrix you can write can be written like this. That's it. And the Hamiltonian has to be Hermitian at each point in momentum space. Okay, so what have I done? I'm telling you that the way to think about a two-band problem is to think in terms of these vectors, n of k. The vectors live on this sphere, but k lives on the torus. So at this point, I should go through a lot of painful topology to work that out, but actually, take my word for it, I can replace T2 by S2 and get the same answer. Not obvious, right? But it's true. So with that, I'm in business because we've already discussed what happens for maps between S2 and S2. So it's sort of funny. I'm applying topology now to classify these band Hamiltonians. I'm saying if there's a 2x2, if I have two bands, any single particle Hamiltonian independent electrons, not interacting electrons I put in it, will be classified by some map of the sphere to the sphere. So there must be an integer's worth of them. There is some trivial map where all the ends are the same, maybe point in the z direction. It looks like the Pauli matrix everywhere. And otherwise, there will be things that will wind. And in fact, these ends will do pretty much what those fermions were doing that I had in the last picture. Okay. So the subject of topological insulators proceeds this way. This is the simplest case. You use somewhat fancier version of this called K-theory. Then you have to worry about disorder and so on and so forth. But basically, you start from here and you make your way up the hierarchy of powerful topological tools. Now, you might say, okay, this is true. Why do I care? Does this have anything to do with anything, right? That would be an utterly reasonable question. And the answer is, well, if you have a non-trivial winding of the Hamiltonian, it has two bands. If you fill one of them with electrons, yeah, you're going to find that the Hall conductance, so electric field this way, current opposite, right, is actually going to end up being given by the winding number times E squared over H. The longitudinal conductance will be zero because there's a gap in the energy spectrum. And so these things end up exhibiting the quantum Hall effect in a lattice, which is not how it was initially discovered. And they're now called Chern insulators. Right? So the same topology allowed us to discover that these Chern insulators can exist with quantized Hall conductance 1, 2, and then plus minus 1, plus minus 1, minus 2, and so on, which has to do with, you literally get the opposite sign of the Hall effect in a given sample. All right. So I think, okay, so I'll just mention this for those of you who are gluttons for punishment, which is that I talked about the Hamiltonian, but actually, I only filled one band. So somebody may be saying, well, why do I have to think about the Hamiltonian? Why don't I just think about the actual state, the wave function? You can, and you can get the same answer. And that requires a different fiber bundle, and that would have required a little more work. Okay, so I'm done. So there are many uses of topology, right? All those spaces we talked about, and we explored a few: defects, solitons, topological terms, and band theory. And then, there's been this huge flood of work, as is often the case these days. The flood of theory tends to outrun experiments, which are much harder to do. But nevertheless, especially with regard to, single electron physics, there's actually been a remarkable amount of experimental work, realizations, materials, clever material physics, most of which I haven't even tried to describe to you. And with that, I will stop. So for the purposes of recording, I'm going to repeat the question, which is to say, the question is, I said it makes a difference, but I didn't explain what the difference is when we add the topological term to the quantum mechanics. So this is, of course, easiest to say in the language of path integrals, but I could just as well do it in terms of Hamiltonians. The energy spectrum will be different, right? So you'll get different eigenvalues. But if you calculated the path integral and you said, okay, so this particular one has a certain circular symmetry. Let's say the energy spectrum is different, which is you get different energy eigenvalues. So in Hamiltonian language, you will end up doing something like either you will explicitly put a vector potential of the flux in the middle and keep periodic boundary conditions, or you are forced to go to boundary conditions in which the wave function has to twist and come back by a factor e to the I alpha, and that is another way of seeing why the eigenfunctions will then come with different eigenvalues. So in the case of QCD, which Andre can describe better, there's a topological term which will then break symmetries and CP violation, things like that. And that's really sort of a descendant of, or ascendant of this simple case. Okay, so the question is, what did I write here? So the first Lagrangian is just 1/2 the mass times the velocity squared, theta rho squared, yeah. And then the action was just that Lagrangian plus the, yeah. Well, let me answer this way, which is to say, there are field theories that people study mathematically, which are topological quantum field theories. Steve's talk will, I don't know that he'll talk about them, but they will be background music, or maybe invisible, inaudible background music to what he's saying. But those are field theories in which they're imaginary quantum mechanical universes in which, yes, everything is topology. There's literally no notion of distance, right? So people study, I think there's some model gravity problems, I think topological. Well, it's not the world you live in. It's simply not the world you live in, right? Because if you live in London versus living in Edinburgh, I mean, it's very clear that it takes longer to get there. So that's why, which is to say, it's all, I mean, it's instructive to study these simple cases. So the topological quantum field theory is, it's actually space-time topological. So both have no clear meaning. The only thing you know is, did you do this or did you not do this, right? Around some, so that the world around us is not topological in that sense. It's not invariant to arbitrary, changes of position and so on. But nevertheless, I mean, a lot of very beautiful mathematical physics, which has been very insightful, actually has gone into exactly the universe you'd like to consider. I plead guilty. Yes. No, absolutely. Helium, not so much, but yeah. I mean, although even in helium in cold atomic, sorry, no, I was supposed to repeat the question. I didn't mention laboratory examples of topological defects. And you're right. Liquid crystals, they're beautiful imaging in cold atomic gases where they have imaged them. You can see them. And you're absolutely right, topological defect. Cosmic strings, I think, are still up for discussion. But absolutely. It's absolutely correct. So the statement is that a vortex-anti-vortex pair is not, from a topological point of view, is not a stable configuration. It could disappear. But if there's an isolated vortex sitting there, it would require you to do something on the entire size of the system. So topology, that was the statement, that topology proposes, but of course the details of physics and energetics still remain. Sometimes, it can happen that you make a vortex, anti-vortex, and they get stuck for some reason. So they're there forever, right? And so from a physics viewpoint, they're infinitely long-lived, even though topology would say there's no reason for them to be there. So topology is really insightful because when you start to deal with complicated order parameter spaces, so liquid crystals, you can have a sphere with antipodes identified. That's not something you're used to thinking in everyday life. Then these formal mathematical results really come into their own because it allows you to identify defects that you wouldn't have been able to that easily get if you were just sitting and trying to draw pictures. I mean, eventually you would, but it's just easier to look up a book.